Welcome to the Deep Dive. For anyone keeping pace with the rapid evolution of large language models, especially in their ability to tackle complex reasoning, we've got some seriously interesting findings to unpack today.
Yeah, absolutely.
A new paper has dropped that investigates just how much supervised fine-tuning, or SFT, can boost mathematical prowess, and the results, particularly on challenging datasets like AIME24, are quite revealing.
That's right. We're diving into climbing the ladder of reasoning, what LLMs can and still can't solve after SFT. This research offers critical insights for us in the field, specifically around the, nuanced ways SFT enhances mathematical understanding.
Right.
And perhaps more importantly, the fundamental barriers that, still exist.
Exactly. This paper essentially lays out a reasoning ladder based on the difficulty of mathematical problems, showing what capabilities LLMs acquire as they climb. Our goal in this deep dive is to extract the core knowledge. What are the specific ways SFT improves mathematical reasoning? Where do the limitations stubbornly persist? And what do these findings suggest for the future direction of LLM research?
And for those who need the quick rundown, maybe just the highlights.
Good point. Okay, here's the crucial takeaway in like a minute. The study identifies 4 distinct difficulty tiers within the AIME24 dataset: easy, medium, hard, and extremely hard. The remarkable finding is that a relatively small amount of carefully structured training data, using what they call an R1 reasoning style, can dramatically elevate performance from struggling to near perfect on medium-level problems.
That R1 style is key. We'll get into that.
Definitely. But when it comes to hard-level questions, simply scaling the SFT data yields diminishing returns, with accuracy plateauing and the extremely hard problems.
Yeah, those are tough.
They remain completely out of reach for even extensively fine-tuned models, suggesting a need for fundamentally different approaches. So a real mixed bag.
Absolutely. And what's fascinating here for us as researchers is the way they've characterized this reasoning ladder using the AIME24 dataset.
Right, that ladder concept.
As you pointed out, they observed a clear hierarchy. Models capable of solving the more difficult problems generally demonstrated proficiency on the easier ones. There's a figure in the paper, figure 1, that visually represents this.
Yeah, I saw that. It shows the averaged accuracy across the questions, ordered by difficulty. Pretty clear trend.
Exactly. It averages various models like Qwen, DeepSeek R1, and others they tested.
And it wasn't just a qualitative assessment. They rigorously categorized the AIME24 questions into those 4 levels: easy, medium, hard, and extremely hard, or X for brevity.
X.
This classification was data-driven, based on the performance benchmarks of different categories of models. The base Qwen 2.532b instruct model.
The starting point.
Models that underwent small-scale SFT, like S1.132b and LLM32b.
The ones with just a bit of tuning.
And the more extensively trained models, such as DeepSeek R1, QWQ32b, and still 332b.
Right, the heavy hitters. And importantly, each model attempted each question 8 times, right?
Yeah. Yes, 8 times. And the reported accuracy is the average across these attempts, which gives us a pretty robust performance measure, I think.
Definitely helps smooth out any randomness. So let's delve into that first significant climb up the ladder. The transition from easy to medium difficulty.
Okay.
The baseline Qwen 2.532b instruct model really struggled with these medium-level questions. It achieved only around 10% average accuracy.
Only 10%, wow.
And failed entirely on half of them, just couldn't get there.
But then we see a dramatic shift, right? With just a relatively small amount of SFT, you mentioned about 1,000 examples.
Yeah, roughly 1,000 examples demonstrating that specific R1 reasoning approach.
And with that, models like S1.132b and LLM32b saw their accuracy on these medium-level questions skyrocket to around 90%.
Around 90%, yeah. Even achieving perfect scores on half of them, it's a massive leap.
Incredible.
With what seems like minimal intervention, relatively speaking.
So what exactly were the crucial elements that unlocked this level of performance? What made that small SFT so effective?
Well, the ablation study, shown in Figure 2, breaks down the minimal requirements. The standout finding is the necessity of at least 500 long, randomly selected R1-style trajectories.
Okay, R1 style. Can you remind us what that entails again?
Sure. This R1 reasoning style, as the paper defines it, is crucial. It involves the models generating a detailed step-by-step solution.
Right, the chain of thought idea.
Exactly, but then also reflecting on those steps and explicitly verifying their work. It's about more than just generating an answer. It's about the model exhibiting a sort of thought process with checks and balances.
Ah, okay. That verification step sounds important. So it's not just the quantity of training data, but the quality and the specific type of reasoning demonstrated in that data.
Precisely.
But here's something quite surprising, at least to me. The specific mathematical domain of the training data, whether it was algebra, calculus, combinatorics, stuff like that, didn't significantly impact the performance on these medium-level AV questions.
Exactly. That was a bit unexpected. Whether those 1000 R1 style examples came from algebra or number theory or geometry, the improvement on the medium-level AIME questions was remarkably consistent. However, the researchers also observed that if they use shorter reasoning sequences or fewer than 500 examples,
Right, below that threshold.
or even a different style of reasoning, like the Gemini-style trajectories they mention, the performance on those medium-level questions dropped off sharply.
Okay, so length, quantity over 500, and that specific R1 self-correcting style seem to be the magic ingredients for hitting that 90% on medium questions.
Pretty much sums it up for that step.
Okay, so these models are suddenly excelling at medium-level problems after this targeted SFT. For us as researchers, a key question arises. Are they all now employing identical problem-solving methodologies? Are they just mimicking one successful path?
That's a great question, and precisely what the researchers investigated. They looked at the chain of thought, or COT trajectories, generated by these models on the medium-level questions.
How did they analyze those?
They employed GPT-4o Mini to summarize these reasoning steps, and then assess their similarity to the solutions produced by DeepSeek R1, which is recognized as a very strong mathematical reasoner.
Okay, using a model to judge another model's reasoning path. Interesting approach. And what were the results? Were the SFT-tuned models essentially replicating DeepSeek R1's every move?
Well, not exact replicas, but the predominant trend was towards highly similar problem-solving strategies. Approximately 50% of the generated trajectories were classified as almost identical.
Yeah, 50%.
And the other 50% as mostly similar to DeepSeek R1's approaches.
So very little variation, really.
Pretty much. And this was observed even in models fine-tuned on data spanning diverse mathematical categories. It suggests that while SFT effectively guides them to the correct answer, they might be converging on a relatively limited set of learned strategies, almost like overfitting to a particular style of solution.
Interesting. So they've acquired a powerful technique, but perhaps haven't yet developed a broad and flexible toolkit of problem-solving skills. That makes sense.
Yeah, it points towards potential limitations down the line.
Right. Now, let's shift our focus to the next level of difficulty, the transition from medium to hard. It appears this is a much more challenging step.
Indeed. Unlike the abrupt jump we saw from easy to medium, the progression from medium to hard is considerably more gradual, more of a slow climb.
Right.
Even after that initial small-scale SFT, the models only achieved around 25% accuracy on the hard questions.
Only 25%, so that 90% on medium definitely didn't translate.
Not at all. There's a notable performance cap compared to models that have undergone much more extensive training, like the full DeepSeek R1 or others mentioned.
What are the factors that make these hard-level questions so significantly more difficult? Is it simply the length of problems or the complexity of the calculations involved?
The paper highlights a couple of key contributing factors. Firstly, hard questions typically involve multiple sequential hidden steps.
Hidden steps, meaning steps the model has to figure out aren't explicitly prompted.
Exactly. Think of it as a multi-stage reasoning process where an error in any intermediate step is likely to prevent reaching the final correct solution. It's like a chain, and one weak link breaks it.
Okay.
Table 1A in the paper, which analyzes performance on the sub-questions of AIME24 problem #1, clearly illustrates how accuracy degrades at each subsequent step.
Makes sense. Compounding errors. What was the second factor?
Secondly, some of these hard-level questions involve steps with higher computational complexity. Just crunching the numbers gets harder.
Like needing more raw calculation power or precision.
Yeah, for instance, calculating the volume of a tetrahedron using the Cayley-Menger determinant, as shown in their Table 1B example for problem #5, presents a substantial computational challenge for these less extensively trained models. They might understand the concept, but fumble the execution.
Right, so it's not just the depth of the reasoning required, but also the inherent complexity of certain subtasks and the compounding effect of potential errors along the way. The paper also discusses a logarithmic relationship between the size of the SFT dataset and the accuracy achieved on these hard-level questions. I think that was figure 4.
That's the one. Figure 4 visually demonstrates this trend. As the size of the SFT dataset is increased, the accuracy on hard-level questions does improve.
Okay, so scaling helps.
It helps, but this improvement follows a logarithmic curve. This implies diminishing returns as more data is added.
So you need exponentially more data for linear gains, sort of thing.
Kind of, yeah. And the accuracy appears to plateau around 65% for models trained solely with SFT, no matter how much R1 data you throw at it, seemingly.
65% ceiling. But some models did better.
Yes. Interestingly, models that incorporate reinforcement learning from human feedback, RLHF, like QWQ32B, or that can utilize external tools like STIL3.
Like a calculator or a symbolic math engine.
Exactly, things like that. Those models managed to surpass this 65% accuracy ceiling.
Okay, that's a critical observation for us. It suggests that simply scaling up the SFT dataset might not be a sufficient strategy to conquer these hard-level problems.
Seems that way.
Alternative training paradigms like RL or integrating external capabilities might be necessary to get past that plateau.
Right. It hints that just learning from static examples has its limits for these really tough, multi-step computational problems.
The researchers even conducted an interesting experiment with a carefully curated, small-scale SFT dataset, didn't they? Selecting examples specifically similar to the hard questions.
Yes, they selected 1,000 R1-style trajectories that were deemed most similar to the hard-level questions, trying to be very targeted.
And did that targeted approach work better than just random examples?
Well, this meticulously curated dataset did yield a marginal improvement in performance, approximately 5% higher than a randomly selected dataset the same size. So a small bump.
Only 5%. Seems like a lot of effort for a small gain.
It does, and crucially, doubling the size of a random data set from 1,000 to 2,000 examples resulted in a larger performance gain than that careful curation. This finding suggests that, at least within this data regime, the scale of the data set has a greater impact than carefully selecting the training examples based on similarity. More data, even if less targeted, was better.
So while targeted data can offer some benefit, the sheer volume of training data appears to be a more significant factor at this hard-level stage, up to that 65% point anyway.
That seems to be the conclusion, yeah. Scale trumps curation in this context.
Now let's move to the highest rung of the ladder. The transition from hard to extremely hard, or X. Sounds like this is where the current SFT approaches really hit a wall.
Absolutely. The paper emphasizes that the X-level questions represent a fundamentally different category of challenge. Notably, as illustrated back in that figure 4.
One showing the plateau.
Yes. All the SFT-tuned models evaluated, regardless of the size of their training datasets, achieved 0% accuracy on these X questions.
0%. Flat zero. That's stark and very telling.
It really is. Complete failure across the board for SFT alone.
So what are the fundamental limitations that are preventing these models from even making progress on these X-level problems? What makes them so different?
The researchers conducted a detailed probing analysis of the DeepSeek R1 model, which, as we said, is a strong representative of these R1-style reasoning capabilities, to understand these limitations.
Okay, what did they find?
They identified several key issues.
Yeah.
One is what they term rigidity in common strategies.
Rigidity, meaning they get stuck in a rut.
Pretty much. LLMs tend to rely on well-established patterns and techniques, for instance, always setting up coordinate systems for geometry problems, or always applying the principle of inclusion-exclusion for combinatorics, standard textbook methods.
Right, the go-to strategies.
The challenge is that these standard approaches may not be appropriate or even viable for the highly unconventional nature of these X-level questions. These problems often require a non-standard insight or trick.
Can you give a specific example from the paper that illustrates this rigidity?
Sure. Consider AIME24 problem #2, which involves coloring the vertices of an octagon in a certain way. The most direct solution involves considering different cases based on the number of blue vertices, a casework approach.
Okay, simple casework.
But DeepSeek R1 persistently attempted to apply the inclusion-exclusion principle based on rotation angles. It's a known technique, but for this problem, it becomes incredibly complex and ultimately wasn't the right path. It just kept trying the same wrong tool.
So it saw combinatorics and immediately jumped to inclusion-exclusion, even when a simpler, more direct method like casework was better suited. That's a clear demonstration of how an over-reliance on familiar methods can be a significant obstacle.
Exactly. It lacked the flexibility to adapt its strategy. What were some of the other key limitations they uncovered?
Another significant limitation is a deficiency in geometric intuition.
Geometric intuition. That sounds tricky for a text-based model. Very. While LLMs can solve certain types of geometry problems, maybe formulaic ones, their underlying sequential, one-dimensional architecture makes it difficult for them to grasp spatial relationships and utilize geometric insights in the same way humans do. We can visualize things.
Right, they don't see the geometry.
Exactly. For example, problem #21 involves counting rectangles within a dodecagon. It's most effectively solved by identifying a few base cases and then leveraging rotational symmetry to determine the total count. You'd sort of see the pattern and rotate it.
Makes sense visually.
But the models struggled to even recognize, let alone exploit, this underlying symmetry. They couldn't make that intuitive leap based on the spatial arrangement.
That highlights a fundamental difference in how these models process information compared to humans, who can often visualize and intuitively understand spatial relationships. What was the third key limitation identified?
The third crucial issue is limited reasoning context.
Even with big context windows these days.
Even with large context windows, yeah. They still struggle with problems that require extensive exploration of numerous interconnected substeps. It's about managing complexity over long chains.
So keeping track of everything.
Right. They might be able to solve a smaller, isolated part of the problem correctly if you prompted them just for that substep. But when faced with the full problem demanding a lengthy chain of dependent reasoning, they often lose track, maybe contradict themselves, or jump to incorrect conclusions.
So it's not just about the difficulty of individual steps, but the ability to manage and maintain coherence across a long and potentially branching reasoning process. That's a tough one.
Definitely a major hurdle.
Okay, so we've explored this reasoning ladder, easy, medium, hard, excels, and it seems we've encountered a significant barrier, a hard ceiling at the very top with those X problems. What are the main insights and implications that we as researchers should take away from this study?
The paper offers a very insightful summary in Section 3 and Table 2. One key takeaway is the distinction between potential and stability.
Potential versus stability. Explain that.
Small-scale SFT models demonstrate the potential to solve a similar number of AIME24 questions as a highly capable model like DeepSeek R1 if you give them multiple attempts, like that 8-attempt average we talked about. Their best guess might be right sometimes.
Okay, so their peak performance isn't bad.
But their overall average accuracy is lower due to a lack of stability in those longer reasoning chains and more complex computations, especially on the hard problems. They aren't reliable.
Right, they might occasionally arrive at the correct answer, but they lack the consistent reliability on the more challenging problems.
Got it. What other key insights did the research reveal?
They also found that the notion of meticulously curating small-scale SFT datasets, aiming for high similarity to target problems.
That 5% boost experiment.
Exactly. That yields only marginal benefits around a 1% overall difference across the board, they found, compared to models trained on randomly selected data across various math categories.
Only 1%. That's even smaller than the 5% on hard questions. So really minimal gain from curation overall. Seems so. Furthermore, the performance across different mathematical categories, algebra, geometry, etc., within these models remains surprisingly consistent after SFT. Training on algebra helped with geometry problems just as much as training on geometry did, essentially.
That's fascinating. It suggests the SFT is teaching a more general reasoning skill applicable across domains, rather than domain-specific knowledge.
That could be one interpretation, yeah. Or maybe it's just teaching that specific R1 procedural approach very strongly.
So what does consistently demonstrate a positive impact on performance then, if not curation?
Scaling the SFT dataset continues to be a crucial factor, challenging claims that very small datasets are always sufficient. You do need a decent amount of data.
Okay, scale matters.
But as we discussed with the hard-level questions, the performance gains from scaling diminish, indicating that plateau. More data helps, but only up to a point, especially for SFT alone.
Right, the diminishing returns.
And finally, the observed tendency of SFT-trained models to converge towards similar solution strategies, that lack of variety we noted earlier.
Yeah, the DeepSeek R1 similarity.
That raises a fundamental question for our field. Can
Yeah.
we truly develop higher-level, more creative mathematical intelligence solely through supervised fine-tuning? This convergence might inherently limit their ability to discover truly novel and ingenious solutions, the kind that sometimes characterize human breakthroughs.
A really important question. Is SFT just teaching mimicry of existing solutions, not genuine, flexible reasoning?
It's definitely something to consider, and the researchers also extended their investigation to the AIME25 dataset, right? Just to check consistency.
Yes, in the Appendix D. Did the findings hold up?
Yes, and the findings on the AIME25 dataset were remarkably consistent with those from AIME24. They saw the same ladder-like structure of difficulty.
Yeah.
The near-perfect accuracy on medium-level questions with the initial 1000 R1 trajectories across different categories.
Right, that's good.
The logarithmic scaling of accuracy on hard-level questions with increasing SFT data and the limited impact of careful data curation, it all replicated quite nicely.
Good to see the consistency. And they looked at generalization, too.
Briefly, yeah. Appendix E provides some evidence suggesting that these small-scale SFT models exhibit reasonable generalization capabilities to out-of-distribution datasets like GSM Plus and HLE, which are different math problem benchmarks.
So the skills learned on AIME problems do transfer somewhat. That's positive.
It is, yeah. It's not completely brittle.
Okay, so to summarize the key insights for our audience, SFT is undeniably a powerful technique for enhancing mathematical reasoning in LLMs, particularly for problems of medium difficulty where it causes a huge jump.
Definitely effective there.
However, significant challenges remain for hard and especially extremely hard questions. These highlight limitations in the stability of reasoning, the ability to deviate from common problem-solving strategies, that rigidity issue, and a fundamental grasp of things like geometric intuition.
Key barriers, absolutely.
And while scaling SFT data does help, especially up to the hard level, its effectiveness diminishes, hitting a plateau. Plus, carefully curating small data sets alone doesn't appear to be a game changer. Volume seems more important initially.
Precisely. This research underscores that while SFT has made significant strides, achieving human-level mathematical intelligence, especially the creative, flexible kind, will likely necessitate exploring training paradigms beyond just supervised fine-tuning on existing solutions. We need something more.
So, given these findings, here's a crucial question for us and for you listening to consider. What are the most promising avenues for future research to overcome these limitations? Could novel training methodologies beyond SFT be the key?
Like what? Maybe more advanced RL, self-play?
Perhaps, or maybe architectural innovations in the models themselves. Models designed differently to handle geometry or long-range dependencies.
That's a possibility too.
Or maybe it's about a more effective integration of external tools and knowledge into their reasoning processes, like those models that broke the 65% barrier.
The better tool use seems very promising, yeah.
It really makes you think about the fundamental gap between the current, somewhat rigid pattern-matching approach of these models and the human ability to devise elegant, often unexpected, solutions to complex mathematical problems.
That's the core challenge, isn't it? Bridging that gap. And that's the critical question that this research really prompts. While the paper provides valuable insights into the current capabilities and limitations of SFT,
Which it definitely does.
the path towards more advanced and versatile mathematical reasoning and AI is clearly an area ripe for continued exploration and hopefully innovation.
Absolutely. Well, for those of you wanting to dive deeper into the specifics of this fascinating research, we'll include a link to the paper, Climbing the Ladder of Reasoning, in the description below.
Definitely worth the read.
We highly encourage you to check it out and consider the implications for your own work in this rapidly evolving field. Thanks for joining us on this deep dive.
Thanks for listening.